right, here we go. Okay, guys, very quickly, we have a couple more formulas to talk about in gases. And again, if your lab is not done, please put it in the tray so that I may grade it. I hope you had worked on it for homework, but some of you, a rumor went around like, he's giving us another day. I never said that, but you know how rumors are. So, you guys investigated this in your simulation and in your lab. PV equals nRT, this is the ideal gas law. And it's pretty straightforward. 5 variables. One of them is a constant, and the rest are pretty easily labeled. The thing you got to remember about Pivner, about the ideal gas law, is the R value depends upon pressure. Okay, volume's always going to be in liters, temperature's always going to be in Kelvin. The R value is going to depend upon pressure. And the reason I say that is in this class, pressure is going to be atmospheres almost always. So I've been doing it long enough that basically everything you're going to get is going to have pressure in atmospheres. So R is going to be 0.0821. But should you get online and watch a tutorial where R isn't atmospheres anymore, they might use 8.314 or 81 or 8314, depending on what the pressure unit is. So in this class, pressure is going to be atmospheres, R is going to be 0.0821. Okay, that's the ideal gas law. Pretty obvious, just a little bit of arithmetic, and you're good to go. So, questions? No questions? Yeah. Move on? Yeah. We're moving on. Okay. So we're going to have to do ideal gas practice because you already done it on our worksheet, and we'll get more. And this is just a diagram out of an old textbook, so we'll skip that. Daltons Law. Okay, so Daltons Law is pretty cool. Daltons Law of partial pressure simply states that the total pressure of a mixture of gases is the sum of whatever each gas exerts. It's really, really simple. People like to make it more complicated than it needs to be, but it's super simple. It's just if you have a mixture of gases, the sum pressure of all the gases is just the sum of the individual pressures that make up a big sample up. So, yeah. And it works for proportions. It's pretty neat. So it means if you have a half an atmosphere of pressure in gas A and a half an atmosphere of pressure in gas B, you put them in the same balloon, they're going to exert 1 atmosphere. 1/2 and 1/2. Make sense? Okay. Now you learned a while back that nitrogen makes up 78% of our air, and oxygen makes up 21% of our air. 99%. And the 1% is everything else. Okay? So, if you had a sample of gas, this sample of gas, see the sample of gas? What is the pressure in this sample of gas?
1 atmosphere.
1 atmosphere. If the total pressure is 1.0 atmospheres, then what is the pressure due to just N2? 0.78. 0.78 atmospheres. And what's the pressure due to just O2?
121.
0.21. Okay? Easy or hard?
Easy.
Pretty easy, right? Now, another example, if you had a sample of gas, and that sample of gas was 3 equal, pretend those are equal, 3 equal parts of argon, krypton, and xenon, and the total pressure was 4, let's make it a really easy number to work with. The total pressure was 2 atmospheres. What is the pressure due to just krypton? 2/3, right? So 2/3 or 0.66 atmospheres. And the pressure due to just argon would be
2/3.
Yeah, 0.66 atmospheres. And the pressure due to just xenon would be
2/3.
0.66 atmospheres, 2/3. Make sense? Okay, now the other application of Dalton's Law has a lot to do with what we did yesterday when we did the water displacement. If you remember, we had the water displacement in the graduated cylinder. And we bubbled gas into the graduated cylinder, and we had C4H10 in the graduated cylinder. Well, here's the crazy thing. For reasons that we're going to talk about in about 10-15 minutes, that's not the only gas that was inside. There was another gas in the container with the butane. What do you think it was? It wasn't oxygen. It wasn't carbon dioxide. Sorry, what?
H2O.
H2O. Good. There was a tiny bit of gas of water vapor above it because we collected it in water. So there's a little bit of water vapor for reasons we're going to talk about in about 15 minutes. A little bit of water vapor that went up into the butane gas. So if the total pressure, what was the total pressure in the container? 1 atmosphere. If the total pressure was 1.0 atmospheres and the butane was 0.95 atmospheres, how much pressure was due to water? 0.05, right? 0.05 atmospheres. And that's really what was going on. Now, there wasn't enough water vapor that you'd notice it, but anytime you collect something over water and do water displacement, there's always a tiny bit of water vapor in your sample. Can you handle this?
Yeah.
If this stuff makes sense to you, give me a thumbs up. If you want to talk about it some more, wave your hand around. Okay. Any specific questions, or do you want me to go over all of it again? Go over all of it. Okay. So Dalton's Law basically says, if you have a whole bunch of samples, if you have a sample of gas made up of various other gases, the total pressure is equal to the sum of the individual gas. So if you take gas A, half an atmosphere, gas B, half an atmosphere, gas C, half an atmosphere, the total pressure would be 1.5 atmospheres. And because of that, and math, you can look at proportions. If 78% of your sample is one gas, then you multiply 0.78 times the total pressure. If 21% is some gas, you multiply 0.21 times your total pressure. And that gives you the individual pressures. Cool? All right, so this is just what we were talking about. Now, let's move on to my favorite gas law, Graham's law. Now, you have actually used Graham's law before. You just didn't realize it was a law. Graham's law has to do with the idea that temperature is a measure of what?
Kinetic energy.
Temperature is a measure of kinetic energy. So temperature measures kinetic energy. And the formula for kinetic energy is 1/2 mv squared. Don't keep me in suspense. Okay. This is a don't worry about it till the end of the day kind of message. Or don't worry about it till maybe not. Yeah, half hour. Okay. So anyway, so temperature is a measure of kinetic energy, which is 1/2 mv squared. And what does that mean? If you have two samples of gas at the same temperature, they necessarily have to have what? The same kinetic energy. So if you look at a sample like nitrogen, N2, nitrogen has a molar mass of 28 grams per mole. Oxygen, O2, has a mass of 32 grams per mole. If they're at the same temperature, then they have to have the same 1/2 mv squared. But are the m's and the v's the same?
No.
No, because nitrogen has a smaller m, it has what kind of v?
Bigger.
A bigger v squared. And oxygen would have a bigger m and a smaller v squared. Make sense? So that's Graham's law. Graham's law basically says, if you know the kinetic energy of a gas at a certain temperature, any other gas at that same temperature has the same kinetic energy. So if you know the molar mass of one gas and the speed of that first gas, you can find out how fast the second gas is going if you know its molar mass. Cool? 4 variables, you know 3 of them. Does that idea make sense? Give me a thumbs up if that idea makes sense. So we're kind of floating around a little bit. Okay, so we usually just show Graham's law like this. Some people like to use square roots. I don't. I just like to say the 1/2 mv squared of gas A equals the 1/2 mv squared of gas B. So the kinetic energy of gas A equals the kinetic energy of gas B if they're at the same temperature. Now there is one more thing we need to talk about. This is called Graham's law of gas effusion. And we need to talk about what effusion is. If you open your perfume bottle, the gas must first effuse out the top. Effusion is direction of a gas in, movement of a gas in one direction. So effusion is movement through an opening in one direction. So before the gas can move around the room, it has to effuse out of the opening. Now, once it does effuse, then it can diffuse. And diffusion is in all three axes. So effusion is how fast gas moves in a single axis, one direction through a hole. Diffusion is how a gas moves in 3 dimensions. Make sense? So when you sneeze, first the coronavirus effuses, then it diffuses. He's trying to be topical again. Does this make sense? If this makes sense to you, give me a thumbs up. That makes sense to me. If you want to talk about it some more, wave your hand around. Okay. So if that's the case, let's do some practice. The first 2 questions are just some conceptual understanding questions. Okay. Don't blurt these answers out. I want you to chat with your neighbor for about 30 seconds. First question. By how much does a gas's sample's energy change if its temperature doubles? You're going to answer, this is a multiple choice question, you're going to answer 1 if it doesn't change at all, 2 if it doubles, and 4 if it quadruples. So chat with your neighbor, take about 30 seconds, and decide how much does a gas sample's energy change if its temperature doubles. All right. If you and your neighbor think that the energy does not change when the temperature changes, give me a 1. If you and your neighbor thinks the energy will double, give me a 2. If you think it's going to quadruple, give me a 4. Seeing lots of 2s in the front row. 2, 4, 2, 4, 2, 2, 4. Looks like about 2/3 you think it's going to double, and it's going to double. Because what is the definition of temperature? Kinetic energy. If you double the temperature, you double the kinetic energy. If you triple the temperature, you triple the kinetic energy. Temperature is a measure of kinetic energy. Cool? Next question. What about the speed? The V in the kinetic energy formula is velocity, which is a fancy way of saying speed. Take about 30 seconds. If you double a gas's speed, how does its kinetic energy change? Take about 30 seconds to chat with your neighbor. Okay. If you and your neighbor think that energy doesn't change if you double the speed, give me a 1. If you think doubling the speed doubles the energy, give me a 2. And if you think doubling the speed quadruples the energy, give me a 4. So 4, 2, 4, 4, 4, 4, 4, 4, 4, 4. Looks like most of you think it quadruples, and it does. Because the velocity here is squared. If you double square something, you change it by 4 times. It's like m double double. Make sense? So double squared is changing something by 4 times. Now that we got that out of the way, let's do some math.
Oh yeah.
If oxygen is traveling at 450 meters per second right now, how fast is nitrogen traveling right now? So if that oxygen molecule is traveling at 450 meters per second, how fast is that nitrogen molecule moving?
The same.
Same?
Yes.
It's possible.
So oxygen, nitrogen has to be traveling as fast as free.
O2 is traveling at 4
Not volume, velocity.
fast, which means it has to be fast.
But also we need to find a number.
You have to mathify it.
Good job on the conducting, but it's the mathematical problem.
Well, yeah. So we'd have to put it in 1/2 mv squared, both of them. So of O2, 1/2 mass of O2 is 16. No, it's not. Plus was 32. Times v squared equals 15. Big number. Oh yeah, 1/2 times 10 That's way too big. That can't be right. I've got 3,543,700.
Oh, well that makes sense.
I feel like that might be. I don't know if that actually.
Yeah, I guess that's what they're saying.
I think I'm waiting.
Yeah, you're right. The calculator has it on this thing. It's very
It's already there.
That's the answer.
It's already written down. Can I just chuck the halves out of the equation? Because it's already there. It's already. Can I just get rid of the 1/2 on both sides? So the molar mass of nitrogen is 28 gram per mole, and then we're looking for Vn2 squared, and the molar mass of oxygen is 32 gram per mole, and we're seeing it's going to move 450 meters per second squared. Does your work look like my work, kind of?
Yeah.
You just started. So some people like to put the whole thing under radicals. If you're like, radical, 32 times 450 squared divided by 28.
No, well, because it doesn't have on both sides.
Yeah, it's a half on both sides, so you might as well just remove it.
Each other.
And do some spring cleaning. This is pretty gross. There is a lot of dust up here. It's pretty gross, all this dust. Now keep in mind, ask yourself when you get an answer, if your answer makes sense. Because nitrogen is more or less or less dense than oxygen? Less dense. So it should be moving faster or slower?
Faster.
It should be moving faster. How much faster? How much is it? How fast is it moving?
481.07.
481? 481 meters per second. That makes sense. 481. So again, square roots are tricky, so put your numbers back in. You got an equal sign in the middle of your Graham's law, so use it. When you have an answer, multiply this side, write down, multiply this side, write down, see if they're the same. Got an equal sign? Okay. Does this make sense to you? Give me a thumbs up if you're with me so far. Okay, it looks like about 2/3 of you. So let's do one more. Now let's look at a gas that is more dense than oxygen. Let's look at argon. How fast is argon moving? Argon has a molar mass of 40 grams per mole. So do the same thing you did with the nitrogen, but now use a more massive argon. Yes, yeah, compared to oxygen.
Which is still moving 450 meters.
Which is still moving at 450 meters per second. Yes.
So now it's still using the 450 meters per second.
And remember, argon is more dense than oxygen, so you would expect it to be moving slower.
You don't square it. You don't square it until
square root the entire.
yeah, 450 squared times.
Square root, then plus 32 times 4.
So for the first more and more zeros. Okay, so 648, so basically I put so you would do the division first.
So if you got a number larger than 100, raise your hand. Good. Larger than 200? Larger than 300? Larger than 400? Larger than 500? Cool. What'd you get? 402 meters per second. Good. I think you guys got a pretty good handle on this. There is one more concept that we need to talk about. So I'm going to put this in the microwave, then we'll go talk about it. All right. I promised I would tell you why there was water vapor in the graduated cylinder yesterday. So now we're going to talk about that. The concept, before we talk about that, I want to talk about this. There's a sample exercise you could be working on, and it says, an unknown gas moving three times slower than oxygen. And people hear this and are like, but it didn't give me the speed. Well, if it says 3 times slower than oxygen, you basically pick whatever speed you want and make the other